Hello once again, ladies and gentlemen, and welcome back to question number 4 on the 2017 grade 11 multiple choice Fermat paper. What have we got here? 8 teams compete in a tournament. Each pair of teams plays exactly one game against each other. Okay. There are no ties. If the two possible outcomes of each game are equally likely, what is the probability that every team loses at least one game and wins at least one game? Okay, so first thing to note, each of the possible outcomes equally likely. This means it's an equiprobable sample space. And so what that really means is we just need to figure out two things. One, how many ways can all the wins and losses occur overall? That's the total number of outcomes. And then we want how many ways can the teams play and win and lose and specifically satisfy the criteria that they give us. Every team loses at least one game, every team wins at least one game. Okay? Then we do the latter over the former, and that gets us our probability. There are no weights here. It's not twice as likely that this team wins or anything like that. Just straight equiprobable sample space. Okay? So, that's something that makes our life a little easier. Probably something you didn't really worry about this if you tried this one, because they don't really do non-equiprobable sample spaces in high school. It's more of a university statistics sort of a thing. But, what could we do here? So we got 8 teams competing in the tournament. If it's equiprobable, let's figure out how many ways there are for all the win-losses to go down in total. So, for 8 teams, each team plays each other. So they said exactly once. Alright. Each team plays exactly one game against the others. Okay. So that means if I had sort of Team A, and, B, C, and D, and so forth, how many games does Team A play? Well, they play against Team B once, Team C once, Team D. So they're going to play 7 games, one against each of the other 7 teams. Team B will play, well, it'll also play 7 games, but one of those is the AB game. So let's not count that game. So it's got 6 games. 6 games where if we listed, X versus Y in alphabetical order, B comes first in 6 of them. C comes first in 5, D in 4, all the way up to H, because there are 7 notes on a keyboard. So Team H will play, well, he'll headline none of the games. So the total number of games played is just going to be this sum right here. Which, you should know at this point, there's a fancy way of adding these up. 7 times 7 plus 1 all over 2. And that's 7 times 8 is 56 over 2, 28 games. Okay. Now, each game, the headliner, which I guess is now a term I'm using, so X versus Y with X is the alphabetically first one. So the headliner can win, I'm going to call this headliner, can win or lose. So that's 2 possibilities, and that's for every single game. Each of these games are independent. So 2 choices per 28 games. That's going to be 2 to the power of 28 different outcomes. And that's a lot of outcomes, like a lot. Which makes me think that, so that's 2 outcomes. So 2 to the 28 possible, I guess these are tournaments. 2 to the 28. That's a big number. I think if I put that in my calculator, it's definitely going to not display it properly. I'll just double check that. Oh, it does. It just barely. 2, 6, 8, 4, 3, 5, 4, 5, 6. Okay. But huge number. And so if we're going to start counting, well, can A win? Can B win? Does B win this game? Well, B's got to win this game, and he's got to lose at least one of these games. That sort of thing. It's a lot of possibilities to work with. So, let's look at a simpler case. When we have trouble because numbers are too big, there are too many teams, we can look at a simpler case. Let's suppose we just had 3 teams. Maybe A, B, and C. So, by our reasoning, we can have 2 times 2 plus 1 over 2. So 3 games, and that's 2 to the 3, or 8 outcomes. So I can actually list all these outcomes out. If I had, by the way, sometimes one case doesn't, one specific smaller case doesn't work. We might have to work with 4 of them. We'd have 3 times 4, so we'd have 6 games. So that'd be 2 to the 6, so that's going to be 64. I'm not going to be wanting to write a lot of these things out, but well, let's take a look at it. So I think probably the easiest way to do this is draw a picture. So yeah. So we'll draw it with I'll draw a directed graph with arrows pointing from teams to other teams. So this means X loses to Y. That's what we're going to have here. So then we can have A, B, and C, and we could have, A win both matches and then B win. This might not be the best way to do it because I'm worried that I'm not going to be able to write out all my possibilities. But we'll see what we can do. We're just messing around. If this turns out to be too difficult, we'll approach the problem from a different way. Or at least we'll try. A wins both, and then C wins. A wins, and then A loses, and B wins. A wins, A loses, C wins. Now we've got loses, 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 and we'll just repeat everything else we saw above. Okay, so that actually wasn't that bad to enumerate them all. So now let's look for, so let's take a look here. So B wins a game, B wins against C, loses against A. So that's fine, that's allowed. C loses 2 games, that's not allowed. A wins 2 games, that's not allowed. A wins 2 games, no. This one's fine. We have a nice little cycle. I'm finding it's easier just to point out that somebody's losing everything or winning everything. In fact, with this case, you'll always, if somebody wins everything, somebody will also lose everything. So, really, we've got 2 out of 8 work. So 2 out of 8 satisfy the criteria. All right, so 1/4. But if we take a look at the answers, I think I saw 1793. These aren't. It's not just going to be 1/4. This doesn't scale up. So obviously there's something going on here. Now if I wanted to do A, B, C, D, as I already said, I get 64 different cases. I'm not going to be able to write them all out. But, yeah, excuse me. Dust in my eyes. Well, dust in my nose, I guess. But if I had, A, B, C, D, I could start drawing more pictures like this. And, this is fine because everybody's winning and losing, but second I do something like this where A wins everything, that's not allowed because A has to have at least 1 loss. So no team can win everything. no team can lose everything. And these were separate with the these were separate conditions. Or sorry, these weren't separate conditions. They were the same condition when it was just 3 of them. Because if you had one team win both of its games, then another team had to lose both of its games. But we can very easily sort of get a little cycle going on here where just A wins. Or, just A loses. So these conditions are sort of separate. So they can occur together, they can occur one on their own. But what we're going to do is we're actually going to do, the probability that we want. So the probability where everybody wins 1, everyone loses 1, is the same as 1 minus the probability of the stuff we don't want. And so this is a useful property to know. Because sometimes, and I think this is the case, the probability of the stuff we want, counting up all the possibilities where everybody wins at least 1, everyone loses at least 1, I think that's going to be very, very hard. I can't even think of a way to enumerate that. Or list them out in a very methodical way. But that, as I say, in order to not have that happen, one team must win everything, or one team must lose everything, or both of those happen. And I think that's going to be much easier to work at, because only one of the teams can win everything, because they play every other team. So if we say A is the winner here, then we don't really care what happens to B, C, and D, because we already know this is part of the failure. So everything else, all the other 2 to the 3 games amongst B, C, and D that can be played, all of them are equally counted in the A wins, and so I think it's going to be very easy to count that. So this is a very useful property. So instead, we're going to calculate a number of ways one team can win. Win all. Number of ways one team can lose all. And both. And those will be separate possibilities. Okay. So there's 8. So we'll do the win first. So somebody wins everything. So there's 8 teams to pick. And we'll say we'll signify them with A, but it doesn't really matter. So there's 8 teams to pick out of the 8 teams that there are. One of those. So we pick 1 out of 8. He's going to be the team, or they are going to be the team that wins everything. So then I don't really care what happens to the B and the C and the D, E, and so forth, because we're going to get arrows coming here. So these are all fixed. So we've got 7 wins. What's left? 21 arrows left, and I don't care how they're arranged. So 2 to the 20. There are 2 to the 21 games where A wins. Or sorry, 2 to the 21 different ways this whole tournament can unfold where A wins everything. Okay. Now, how about all lose? It's going to be the exact same things. 8 teams. We pick one of them. Pick one of them. We'll denote it by A, but it really doesn't matter who he is. And we're going to have 7 losses. So the arrows are pointing away. And then what happens amongst the other teams? I don't really care. Anything can happen as far as I'm concerned. Because we already know this isn't going to be one of the things that we like. So 7 arrows already taken. That leaves 21. 6 plus 5 plus 4 plus 3 plus 2 plus 1 plus 0. 2 to the 21 ways for A to be the complete loser. So that means 8 teams to pick. So we might even do 8 choose 1, although I try not to use choose notation. But there's going to be 8 teams, 2 to the 21 ways for them to be the complete winner, plus 8 teams times 2 to the 21 for that chosen team to be the complete loser. And now, what happens about win and loss? Well, if you've done problems like this before, you'll know that there's a possibility that A could be, the complete winner, and that B happens to be the complete loser. That's one of these scenarios over here. That's one of the 2 to the 21. Okay, and so what would we'd have 7 losses, and we'd have 7 wins, although one of these arrows is going through here, so I guess the point is 13 arrows already accounted for, so that leaves 15 games undecided. So that's 2 to the 15 right there. But this is an overlap between these two. So if we want without each team getting a win and a loss, so that's going to then that's the number of games with somebody who wins everything, plus the number of games with someone who loses everything. But inside both of these, and you can sort of think of it as a Venn diagram, all the games that have somebody who wins everything, all the games that have somebody who loses everything, there's going to be an overlap where, if X wins everything and Y wins everything, there's an overlap here where X wins everything and Y loses everything. And we don't want to count that twice, in the X all win and also in the Y all lose. So we have to subtract off that extra little overlap. This is called the principle of inclusion and exclusion, minus number of games with somebody who wins everything and someone who loses everything. Okay. Now I've already spoken. Each of these is 8 times 2 to the 21. But what about the games that we just talked about, where you can have A be the winner and B be the loser, like the super loser? Well, there's 15 games left undecided in here, so we have 2 to the 15. And then how many choices do we have for A and B? Well, we have 8 choices for whoever's going to win. And then of the remaining 7 teams, we have 7 choices for whoever's going to lose. Okay, so we've got 8 times 7 times 2 to the 15. Right? You might think, well, you're just choosing A and B, but the order of them matters as to who wins and who loses. So this is a nice, neat expression, and we could even generalize it to n teams. You could have n times 2 to the n minus 2, n minus 1, all over 2. And you'd have twice that, and then minus I don't know why exactly I'm choosing to write this, but you'd have minus this, and then the order would matter, and then you'd have n minus 3, n minus 2, all over 2. So this would be a nice generalization to n teams. And so this wouldn't be a bad Hypatia question, frankly. So this is the total number we've got, and it's going to be over the total number of games we can have, and that's going to be the probability of stuff that we don't care about. And then we'll just do 1 minus that to get the actual answer. Okay. So, unfortunately, we've got a lot of powers of 2, so things should go fairly nicely here. So the probability that we don't want is 2 times 8 times 2 to the 21 minus 8 times 7 times 2 to the 15 over 2 to the 28. Right away, I can see I can divide by 2 to the 15 on the top and bottom. And we're going to get 2 times 8 times 2 to the 6 minus 8 times 7 times 2 to the 0 over 2 to the 13. We can divide by 2 to the 3 with these 8s, so it'll be 2 times 2 to the 6 minus 7 over 2 to the 10. And that 7 is going to stop us dividing by 2, so it's going to be 128 minus 7 all over 2 to the 10, or 121 over 2 to the 10. 2 to the 10 is 1024. So that's the probability we don't want. So the probability that we do want is everything else. So it's 1 minus this probability. That's going to be 1024 minus 121 over 1024. And so 4, we get a 3 here. The 2's cancel out, we'll get a 0. And the 10 minus 1 is 9, 903. I don't think I saw that. It ends in an odd number, so we can't simplify. And yeah, because the numbers are pretty high. No, there it is. It's D. Alright. I was worried maybe my logic had fallen through, but oh, there we go. We got D. D is our answer. So 903 over 1024 is going to be the probability that every team has at least one loss and at least one win. Okay, so that was an interesting little probability question. I wonder if there was a way to do the straightforward probability computation, like count the things that we did care about, divide by the total number of things. We instead had to switch it up because I thought it was easier to count the things that we didn't want to have happen and then do 1 minus that at the end. But I don't know. If you found a way to add it up, I would love to hear about it. And maybe there are solutions up online have a nice way of doing it, but it worked out. So what we needed? We needed equiprobable, although most people probably wouldn't care about that. I needed sort of triangular numbers to figure out how many games were played, and then it was really just how can the condition fail, and that turns out to be an easier thing to count up. So that does it for question number 24. I will see you guys in the next video as we wrap this Fermat paper up with question number 25. So if you haven't already, I encourage you to try question 25. It should be the hardest question on the contest. So practice it, try it on your own, and then I will see you guys in the next video for that one.